Okay, so today I have the honor of introducing you the Plasma Physics Initiative visitor. He'll be giving a colloquium today on new perspectives of diagnosing electron energization in magnetic reconnection. Dr. Jason TenBarge got his PhD from the University of Texas in Austin, went and got his postdoc at the University of Iowa, where I was a grad student at the same time. He then went on to be a researcher at the University of Maryland and is now currently affiliated with Princeton University, as well as the Princeton Plasma Physics Collaborative. And so rather than take more of your precious time, I'll just hand it directly over to you.
Great, thank you, Chris, and thanks everybody for coming and inviting me. I've structured this talk to have lots of introductory material because I know you're a very diverse group of researchers here. So I'll start with some broad overview sorts of topics here, even introducing what reconnection is, because I don't know if all of you are even familiar with magnetic reconnection and plasma physics. So the basic idea of magnetic reconnection, if you have two oppositely directed magnetic field lines, whether they're components of a total magnetic field, in other words, it's a guide field, or it's just total anti-parallel reconnection, as they come together closer and closer, once they reach each other, those oppositely directed components of magnetic fields, they can then reconnect, snapping and releasing magnetic energy in the form of tension, blowing out the ends. But along with that release of that incoming magnetic energy, we also heat and accelerate particles. This is actually a really common process. Just a few things close by. Magnetic reconnection is responsible for a lot of the really explosive phenomena that occur in the heliosphere, starting at the sun. Things like coronal mass ejections, solar flares, prominence eruptions all occur due to magnetic reconnection happening on the sun. So this is solar dynamics observatory images. So that blast of plasma you saw flowing off there, that energy and this, most of these things are due to magnetic reconnection occurring. So when that happens, you get a blast of energetic particles coming away from the sun, some squirt back down into the sun, of course. And you also get a release of plasma into the heliosphere. Some of that comes towards us. Schematically, that reconnection looks very much like what I showed on that first slide. You squeeze magnetic field lines together, you reconnect, some of that energy snaps back down into the sun. So you could see in some of those SDO movies, the plasma was flying back down into the sun. But much of that energy is actually released into the heliosphere, coming towards us in the form, again, of coronal mass ejections, high energy particles. And in addition to those sort of explosive phenomena that reconnection is responsible for, it's also probably responsible for heating the corona. This is a really long-standing problem in heliophysics. So the photosphere of the sun, which is what we see with our naked eye, don't stare at the sun, please, is about 10,000 Kelvin. That's, of course, heated from the center of the sun where nuclear fusion is occurring. But it turns out the atmosphere of the sun, solar corona, is actually millions of Kelvin. While the heat source is at the center of the sun, somehow the atmosphere is hotter than the surface. It's very strange. One of the likely candidates for heating the corona are what are called nanoflares, which is small-scale reconnection happening all over the surface of the sun, heating plasma, and eventually heating the corona, and also generating solar wind, which is hot plasma always flowing out of the sun. So as things flow off of the sun, we have coronal mass ejections, solar wind, and so forth, that eventually will come to the Earth, interact with Earth's dipole field, or the Earth's magnetosphere. Fun movie. As it impacts the Earth, we can then have magnetic reconnection at the magnetosheath in front of the Earth, depending on the orientation of the interplanetary magnetic field and solar wind. That can also squeeze down and create magnetic reconnection in the tail. And that magnetic reconnection can then accelerate particles. These are, again, solar particles that come down, hit the Earth, and generate things like the aurora. So the aurora are generally high-energy solar electrons and protons that hit the ionosphere and create glowing plasma. So other than all of these fun explosive things, reconnection plays a role in plasmas throughout the universe. And that's through turbulence. So turbulence broadly is injection of energy at large scales it through nonlinear processes cascades things down to small scales. So one of the big questions of turbulence is how do you dissipate that large scale energy that's reached small scales? So this is a prototypical power spectrum for the solar wind, where this is the energy injection range. This is where energy is being cascaded through what's called the inertial range. And then down here is where things usually are considered to be dissipating at scales starting around the ion gyro radius, or inertial length, and going down to the ion and electron scales. What's actually doing the dissipating down here may very well be turbulence. This is a cut of a prototypical turbulent simulation. The colors are magnetic field contours. And all of these X points that are marked on here are saddle points of the magnetic field where reconnection might be happening. Zooming in on one of these boxes, you can see where all of these magnetic field structures look, again, very much like the prototypical reconnection signature that I showed. So something like turbulence is ubiquitous in the universe. It's in the solar wind, in the magnetospheres, all planets, ISM, accretion disks around every object you can think of, intergalactic medium everywhere. Basically everywhere you can stir a plasma, you're going to end up having turbulence. And reconnection probably plays a role in heating all of these plasmas. So just kind of an overview of where reconnection is important. You have things on the sun, where you can heat the corona, generate all these explosive events in Earth's magnetosphere. It's also very important for lab experiments, especially for fusion, where in a fusion experiment, of course, you want to confine your plasma. But if you have magnetic reconnection, that can actually cause a loss of confinement, and your fusion plasma can be squirted out towards the wall of your fusion device, which is very bad, obviously. But it's also important for high energy astrophysical objects. It can generate things like X-ray flares and pulsar nebula, active galactic nuclei, jets, and things like accelerating electrons and accretion disks around black holes. Okay. So I hope I've convinced you that reconnection is important in the universe. So just a quick outline of where I'm going to go in this talk. I'm going to start by introducing the traditional framework for analyzing energization and reconnection. And that's using something called the guiding center framework, and that's done through particle and cell simulations, so I'm going to introduce all of these things. And then I'm going to compare and contrast Lagrangian versus Eulerian energization. Turns out this is actually really important and has been overlooked through the years. And then I'm going to describe the Jekyll simulation framework, including continuum Vlasov-Maxwell simulations. It's something unique. Actually, one of my collaborators on this, Jimmy Juneau, gave a talk here a couple of years ago on Jekyll. And then finally, I'm going to present Jekyll simulations and analysis of electron energization with moderate guide field reconnection using both methods, this guiding center and Eulerian analysis techniques. Okay. So like I said, I'm going to begin with an introduction of PIC results and what particle and cell actually means and is, because that's kind of germane to understanding these two different perspectives. So what is the particle and cell or PIC algorithm? Most plasma physics, kinetic plasma physics, starts from the Vlasov equation, which describes the evolution of the distribution function of particles, ions or electrons, in 6-dimensional phase space. So it's a function of both position and velocity, subject to the Lorentz force. Pretty straightforward. However, this is a really expensive equation to solve. I am going to solve it directly later, but it's expensive, and that's not what is usually done. So instead, let's solve it along characteristics. So we have equations of motion for x and for v. This would describe the position and velocity of particles. Right, that's a single particle sort of evolution in what's called a Lagrangian framework. Lagrangian means you're following individual particles or fluid particles. So each particle here is actually a superparticle. It's not, you can't actually simulate 10 to the 20 particles or however many you have in your simulation. So you might simulate a billion particles, a trillion particles, so that each of these particles that you're evolving represents millions or billions or even trillions of particles in the real system. That means there's going to be counting noise compared to the real system, which is a real problem with PIC simulations. And also the fields, these E and B fields, are not directly computed between individual particles, because that's an n-squared operation for every single particle, and that would be obscenely expensive. So instead, you solve Maxwell's equations by collecting your particles on a grid for the current and the charge density. And again, Maxwell's equations must live on a grid because you have divergences of kernels. So you have particles that live in continuous space, fields that live on a grid. That leads to aliasing errors, which I'm more than happy to talk about. But the main point is this pick algorithm is following particles. Okay. Now, guiding center motion. Okay. So generally, how do these particles move in a magnetic field? If you have a charged particle in a magnetic field, it's obviously going to gyrate around the field. It will also slide along magnetic fields. It might also drift across magnetic fields. If the gyro radius, this circle the particle is making around the field, is small compared to other scales in the system, then you can do something called the guiding center limit, right? So instead of following the particle motion around here, what you're actually going to follow is the guiding center position, right? That makes things much simpler in a lot of ways. You're basically going to average out that gyro motion and just follow the guiding center. So now how does that guiding center move? So if we have our charged particle circling a magnetic field, if we apply any sort of force to it, it's going to create a drift, which could be an F cross B divided by Q. So that means if there's a force downward, magnetic field out, electrons drift this way, ions drift that way. The most prominent drift in a plasma is the E cross B drift. That's just from F equals QE. Just plug that in. This is the, like I said, dominant drift, always. In this case, it's not charge dependent, so the particles all drift in the same direction, meaning it generates no net current. You can also generate drifts due to magnetic field structure. So if you have, say, a gradient of magnetic field, the gyro radius then is different for one part of the domain to the other. So you have net drift due to that gradient in the magnetic field. And this time it is charge dependent. And the other drift that I'm going to be talking a lot about is curvature drift. So if you have a curved magnetic field line like this, then again, you have a difference in the strength of the magnetic field from one side to the other, and then you end up with a net drift. In this case, for the ion, the net drift would be into the page, because it's B cross B dot grad B, or B, this little b is the magnetic field unit vector, and kappa is the curvature of the magnetic field, and kappa points in towards radius of curvature. Okay. So, background out of the way. Okay, so now I'm going to talk about the Lagrangian approach to energization. This is what's traditionally done using particle and cell simulations to describe guiding center motion. So we're not describing particles anymore. We're talking about guiding centers. It's been used extremely successfully for the past 10 years or so, both in reconnection simulations and some turbulent simulations, and it's been applied some in spacecraft data as well.
Can I just ask one question? So you were describing your plasma and the electric fields and everything arising from currents and charge densities. So that would mean you're treating the electrons and protons differently, right? Is that right?
But I mean, in this case, it's PIC. So yeah, you're evolving ions and electrons.
So and so and then you're doing guiding center. The electrons have a much smaller gyro radius. So
Yes.
I'm just wondering about the electrons. Yeah.
Yeah. Okay. That's a good question. I kind of skipped over that. So for this, as the title suggests, we're going to focus on electron energization. For reconnection, as long as you have a moderate guide field, like 0.1-ish is kind of the lower limit, the electrons stay pretty well magnetized throughout the entire process. So guiding center actually works pretty well. I'm going to show you that it doesn't work great in a minute. But yeah, that's a good question. Anything else?
This question? Yeah, I mean, so you gave some examples of forces causing drifts, obviously, in different. Sometimes in astrophysics, gravity is an important force.
Yes.
So, or is this only in relativistic astrophysics that would cause a sort of gravity would cause a drift of?
Usually, yeah. I mean, gravity does cause a drift, but it's small usually compared to everything else. Yeah. Gravity usually enters more directly in the momentum equation for the plasma. If you're evolving it as a fluid, then you'd see a force in there that would actually cause bulk motion of the fluid rather than affecting individual particles.
I also noticed you didn't use the relativistic equation of parts.
This is not a relativistic talk. If you're interested in relativity, I'm sorry.
I'm not interested because I think a particle will be accelerated to high energies.
Yes,
Maybe relativistic effect.
yes, they will be. They will be. So PIC codes are always written in terms of special relativistic. They include special relativistic effects. PR is not generally in a.
I'm talking about special relativity.
Yeah, exactly. But yes, the PIC codes all have special relativity in them, so they can accelerate particles to very high energies, which is what I'll show in a second. Go ahead.
Yeah, but your equation doesn't contain relativistic Lorentz factor. I mean,
It doesn't. That's true. I didn't write that
Yeah,
there,
okay.
but yes, the PIC code itself is self-consistent in that it has special relativity. Good question. Anything else before I move on to actual physics rather than background? Okay, great. And feel free to interrupt me at any time. Okay, so this guiding center approach begins with the guiding center energy evolution equation for a single guiding center. This is from Northrop. Okay. So this is the time evolution of the guiding center energy. So this is the parallel energy. This is the E cross B drift. So this is the motion of the guiding center, the dominant motion of the guiding center. And then this term comes from the energization due to the average gyro motion of the particle. Okay. Where this mu is the magnetic moment. So it's MeV perp squared over 2B. Yeah, and then we have the grad B drift and the curvature drift. Right? Okay. So what are all of these different terms? This first one is often called direct acceleration. So if you have a particle that comes in to a reconnection region where you have a strong E parallel, generally you don't have strong E parallels in plasmas, but where you have a reconnection site, E parallel is actually what supports the current, excuse me, in the reconnection region. So in here, you can just get directly accelerated particles. They just slide right along the field and you can accelerate them like mad. This term is betatron acceleration. It basically follows from conserving the magnetic moment because we're assuming things are magnetized. It's the only way we can apply the guiding center formalism. So if you have a particle that enters a region of stronger magnetic field, it means B goes up. To conserve this variable, it means the perpendicular energy must also go up. Or if B goes down, perpendicular energy must go down, which is typically what happens in magnetic reconnection. And the last one is curvature drift. I already kind of wrote down what it does, but more broadly, and the more interesting thing that it does is it contributes to Fermi acceleration. Okay. So if you have a particle coming in here in, say, a magnetic island, it's flowing along the magnetic field line. This is snapping back at the local alphane speed, or sorry, upstream alphane speed. So it's like a particle reflecting off of a moving wall. So it comes in with B and leaves with B plus 2A. So if you can go through multiple islands like this, you can accelerate a particle quite a bit and generate things like cosmic rays in the case of protons, or simply just high energy electrons. And this is what the curvature term does. So as you can already guess, this generates more higher energy particles than this. And then the trick that is usually done in the guiding center approach is to sum over guiding centers in a local region. Okay, so you're just summing over an ensemble of guiding centers. So you get the total electron guiding center kinetic energy equation, which is this guy. So this is the rate of change of the energy. The parallel energization, I'm going to combine the betatron term and the grad B terms, and then we have a curvature drift term. You can already kind of see something strange happening. We were talking about guiding centers, even though we're actually in a PIC code involving particles. And now we've integrated over some of these particles, and now we have fluid quantities here. This is the perpendicular pressure, perpendicular to the magnetic field, parallel pressure, density, and parallel flow velocity. So we're no longer following particles or guiding centers. We've now taken a step back, and we're standing beside the river, and we're doing an Eulerian picture following fluid variables as a whole. But we haven't actually done that transformation in a formal way. But this is what's been done so far. Okay, and by examining each one of these terms independently, we can see how or what the dominant energization mechanism is in, say, a particle and cell simulation, or it's been applied to spacecraft data as well. So what does this look like in a simulation? So this is a 2D PIC simulation from Joel Darlene's work from 2014. The colors here are the curvature drift term. This is the parallel electric field term. I'll start with the parallel electric field. You can see that it's very splotchy, alternating between red and blue throughout most of the domain, except at these X points where it's dominantly positive. So it's not very space filling. It's mostly just happening here. Whereas the curvature drift term is mostly positive, especially where the field lines are curved, obviously. And then these islands where you have that Fermi acceleration happening, going bouncing back and forth in the island. You might also notice this is 5 times larger than this. Okay. Co-located with these energization terms, you also get an increase in the parallel and perpendicular temperature. There is more of an increase in the parallel temperature than the perpendicular, which you can kind of see by eye here. You can also integrate these various terms over the entire domain. So the red here is the curvature drift. The black is the total energization, dP/dt. Green is the parallel. Cyan, which is barely visible, is the betatron, and blue is the grad B term. So really the only one that matters is curvature drift. It's large and positive. If you sum up all of those terms, it's the dashed line. It agrees reasonably well with the total energy, rate of change, total energy. Looks good. You also generate high energy particles, which is what you're asking about. So plotted here in 3 different colors, purple, red, and black, is the particle distribution function at t equals 0, 50, and 350. And solid is p parallel, and dashed is p perp. So you can see that you do sweep out a high energy tail. This is plotted in log linear space, so you do sweep out a high energy tail. And you also generate much more parallel, generate much more of a parallel tail than a perpendicular tail. Just looking at the black lines. Fantastic. Okay. So it does seem the curvature drift generates high energy particles. Fantastic. If you do this in 3D, it works even better because you're not just bouncing around in single islands. Now you can leave this island and follow these very stochastic field lines that develop in 3D reconnection up to a new island and keep accelerating over and over in that Fermi sort of process. So in 2D, Fermi reflection is just large near where the field lines are contracting in. But in 3D, you can see it's quite a bit more volume filling because you can sample so much more of the volume. You generate even more of a power law tail in 3D than in 2D. And interestingly, if you look at the average rate of change of particles as a function of energy, the parallel energization term dominates at low energies, but the Fermi acceleration term dominates at large energies. Okay.
That holds for both 2 and 3D, or is that just the 3D?
That holds it 2 and 3D, but I think it's even stronger in 3D. Yeah. So actually, it seems like the parallel seeds the Fermi acceleration. So just a quick summary of that before we move on to anything else. So the guiding center analysis indicates that curvature drift or Fermi acceleration dominates electron energy, energization, and weak to moderate guide fields. It's mostly in the parallel direction. That's consistent with Fermi acceleration. High energy particles, meaning tails of the distribution function, are generated, and it's more efficient in 3D than 2D. But again, PIC involves particles, not guiding centers. Turns out that means there's some unaccounted for energization. And also, we only included the grad B drift and the curvature drift. There are other drifts. There are quite a few other single particle drifts that one could include in the guiding splinter description. And by integrating over ensembles of particles, we've kind of mixed Lagrangian and Eulerian perspectives, which kind of, it ends up leading to some misleading impressions. Okay. Any questions before I move on to Eulerian stuff?
Ask about the 2D or 3D, because that's, I mean, obviously always interesting for lots of problems. So I mean, my obviously incorrect thinking is that in 2D, you might be trapped in these islands and that might be more efficient. And in 3D, you would get out, but that's not what happens. So
yeah, it's not quite what happens because there's only so much that the island can contract, a single island. You also need, if it's slow, then you conserve magnetic moments and you don't actually generate high energy particles. So you actually, it's much more efficient if you can leave this island and go into another one and spring back here, and so forth. Yeah, you just have many more opportunities to accelerate versus a single island. Anything else? Yeah.
What are the boundary conditions of the simulation?
That one was fully periodic, I believe.
Ah, okay.
So just a quick review. I expect everybody here knows the difference between Lagrangian and Eulerian. The Lagrangian picture you're following in positions of individual particles or fluid parcels. That's useful for telling you things about particles and individual fluid parcel motion. Whereas in the Eulerian frame, it's like standing at the bank of the river and you're watching things on a fixed grid. So the Eulerian picture is useful for telling you things about bulk fluid quantities like temperature, pressure, bulk flows. And you can say things about particle distribution functions rather than single particles. All right. So the Lagrangian approach seems to have been pretty successful. Lots of people apply that approach to detect electron energization in simulations of spacecraft. But spacecraft data is in a Eulerian frame. You're not actually following single particles in a spacecraft. And continuum simulations, like the Jekyll simulations I'm going to show later, are Eulerian because we're involving F, not single particles. Same is true for like a two-fluid simulation or anything like that. So instead, let's again take an Eulerian approach. So instead of doing guiding centers or anything like that, we're just going to start at the momentum equation, right? So this is the full momentum equation for a plasma, ignoring collisions, touch that. So this is the evolution of the flow velocity. This P is the full pressure tensor. It has gyrotropic or CGL pressure tensor, which you can write in this way, so that you have P perp along the diagonal, and then pressure delta P, pressure anisotropy, which is P parallel minus P perp in the BB direction. This pi is the pressure gyrometry. It's just whatever's left over. It's the off diagonal portions of the pressure tensor. If we want to get the drifts from this, we can do it in a very rigorous way. We just cross this equation with B. Voila, we have all of the drifts. This is all of the perpendicular motion rigorously. E cross B drift. This is what's called the diamagnetic drift. It's due to pressure gradients. This is now the curvature drift. This is the agyrotropic drift due to pressure agyrometry. And this is the polarization drift, which is due to, in a single particle sense, it's due to the rate of change of the electric field, but in a bulk sense, it's actually due to flow velocity. Okay. And then we can easily compute the energization from these drifts. Just multiply this by Qn to get a current, and dot that into E. And voila, a rigorous description of the drifts in a fluid. So parallel energization, just like before, diamagnetic energization, curvature drift, agyrotropic drift, polarization drift. No approximations have been made at this point. This is just rigorously everything that's happening in the plasma. Okay, so let's compare these two really quickly. So this was the guiding center description. This is the Eulerian description. Obviously some pretty big differences. We have appearances of entirely new terms in this diamagnetic and agyrotropic drift terms. These only appear from an Eulerian perspective because they're bulk effects due to how the pressure evolves. Single particles don't know anything about pressures. One of the other big differences is the coefficient on the curvature drift. This is just P parallel plus this M NU parallel squared term. This is just delta P. So in the guiding center framework, basically if you have pressure, isotropic or not, you're going to have curvature drift. In the Eulerian picture, you actually need pressure anisotropy to have curvature drift. This term is actually hidden inside the polarization drift, which is small, as you might expect for electrons because they're small mass. So we don't bother to separate it here because that's quite artificial. Okay. Any questions at this point? Okay, we can try to reconcile some of these differences by manipulating guiding center formulation. I don't really recommend doing this, but you can to try to see how things are connected. The betatron term is the dBdt term, which is just b dot dBdt. dBdt is just minus curl E. And we know E in the guiding center formalism is E parallel plus UE cross B. And then we can manipulate things, plug that back in, and we can get a manipulated version of equation 1. And we can even express the fluid equation into something similar. So now This manipulated guiding center equation now does have a p perp minus p perp ue dot kappa. It has this compressional term and it has this extra parallel acceleration term. It's called the Banyos drift. This is quite an artificial thing to do because you don't usually think of compression as energizing single particles, but you can do it to try to connect these two pictures. On the fluid side of things, I'm going to now name this the beta term, this ue dot grad p, which is the diamagnetic drift, and this new p perp ue dot kappa term to mirror this. Going to have a separate p parallel ue dot kappa, which is curvature 2. We still have the ageroentropy and polarization. I know these are a lot of terms. They'll be a little bit more clear when I actually plot them. You can't see it here. I am going to occasionally separate out this term as a betatron curvature term with minus p perp ue dot kappa, just for analysis purposes. Okay, with that, these two pictures are kind of connected. The final thing we can do to try to connect them is to try to get something that's like a diamagnetic drift in the guiding center equation. So if you note, I mean, divergence of p perp ue is, of course, p perp v plus v dot grad p perp math, integrating that over all space and assuming there's no source of perpendicular pressure coming into your plasma or your simulation, then this compressional term that appears in the guiding center equation is actually equal to the diamagnetic drift term, but only integrated over the entire box. That highlights one of the problems with the Lagrangian picture when you're, or the guiding center picture when you're trying to apply it to an Eulerian plasma. It's really only valid if you've integrated over the entire box. You can't just integrate over local ensembles of particles and say you're good to go. You actually need to integrate over everything. Okay, so that leaves it mostly complete, except we have new terms in the Eulerian picture for the ageroentropy and the diamagnetic drift, because those have no counterpart and no way to compute them from kinetic center. Despite this, there's a lot of ambiguity. As you probably gathered, probably pretty confused at this point because I have like 4 different forms of the energization, 3 different forms of the curvature drift. That's part of the problem with all of this, is how do you actually account for this? How do you group terms? What do they mean? Okay, so that's what we're actually going to try to explore here in some Eulerian Blasov-Maxwell simulations using the Jekyll simulation framework. I have a few slides on Jekyll, the kind of advertisement slides more than anything, but we're going to spend a few minutes here. So Jekyll is a simulation framework we're working on primarily at Princeton, but at several other institutions. It's open source, closed development. You can download it right now. We have an extensive documentation website. We also have extensive post-processing suite called PostJekyll or PJekyll. It's written in Python, makes analyzing the data very easy. It's meant to be a general purpose plasma physics simulation framework. I'll say a little bit more about that on the second slide. It has a diverse array of solvers. The main goal is to develop new algorithms. So these are some of the algorithms papers on doing continuum Blasov-Maxwell that we've written. We've also employed a lot of modern software engineering techniques from other fields that haven't quite caught on yet in plasma physics. And that means we have some unique scientific applications we can actually use this Blasov solver for, including things like diagnosing perils of noise, which I think Jimmy actually talked about when he was here a couple of years ago. So what are the models within Jekyll? Like I said, it's a flexible framework of solvers. So the simplest one is the multi-fluid, multi-moment model, and that's done with the wave propagation finite volume scheme. So we have both 5-moment and 10-moment sets of equations. 5-moment involves density, momentum, and energy. So that's 2 fluid for an arbitrary number of species. We have the 10-moment set of equations, which now also involves the full pressure tensor, which we close on heat flux. We have a variety of different closures that Jada is actually exploring the effect of on temperature and isotropy instabilities as we speak. And more germane to this talk, we have a Blasov-Maxwell solver that directly solves and discretizes the Blasov-Maxwell equation using discontinuous Galerkin method, which I'll say a few things about in a second. And of course, that means we also have Maxwell's inductions equations because these are coupled to E and B. We have to solve those. We also have a gyrokinetic model, and we have other models too, like MHD and Hasekawa-Mima and all kinds of stuff. For this talk, I'm going to focus on the Blasov-Maxwell model. So first of all, what is discontinuous Galerkin? It's a lot of words. It's what we use to discretize the Blasov equation and the E and B fields. The basic idea, it combines the best aspects of finite volume and finite element. So finite volume means you get the things like locality of data because all you're transmitting between different cells is the fluxes between each cell. So it's local, easy to parallelize. You also get stability enforcing limiters if you want to use them. But in each cell, you also have finite elements for higher order accuracy. So you could just do piecewise constant, discontinuous functions to represent this green function in each cell. That would be a terrible representation of the solution. You could do piecewise linear, so that's a first order approximation, or piecewise quadratic, which is typically what we do. So basically in each cell, if you do a quadratic function, you have 3 points in each cell effectively. Okay, so you have 3 times the resolution, the nodal resolution and cellular resolution. All right, so what does the Blasov equation look like when you actually try to solve it this way? So starting with the Blasov equation, you start with a phase space mesh T with cells K sub J. Then you multiply this by your basis functions W, those polynomials that I showed in the previous picture, and integrate and manipulate things. So you have your evolution of your F sub H, which is an expansion of the distribution function in these basis functions. So you have a coefficient that depends on time, and then your basis functions are the functions of phase space. These are fixed, these don't evolve, they are just the basis functions. This is your flux term between cells, and this is the volume term. The volume term comes from here, flux term comes from there. Okay. This scheme conserves things that you want to conserve, like number, density, and energy. For upwind finite differencing, the alternate norm of the distribution of K is monotonically. That just means entropy increases as you expect it to. We've done everything we can to reduce cost because as you would expect, this is an expensive thing to do. So it's a C backend with LuaJIT front end. So it makes it very easy to change and modify input files. We use computer algebra pre-generated kernels. That removes all of the loops and things, makes everything much cheaper and less prone to error. We use MPI and MPI3 shared memory, and we also have GPU parallelization with CUDA, and we use reduced modal basis sets. One other advertisement slide. I have to go through this quickly, but I think some people here might be interested in this. Doing full Blasov, even though we've done everything we can to make it cheap, it's still expensive. So we're also working on a reduced form of the Blasov set of equations we're calling the parallel kinetic perpendicular moment model, PKPM. So this all starts, if you take your distribution function and say you maybe expand it in terms of Laguerre polynomials for B perp and Fourier for gyrophase, while just keeping everything as it is for the parallel component, right? So we haven't done any approximations here yet. But what if we really only need a couple of these coefficients? Right? So that might be the case if your system is, say, strongly magnetized, like around a magnetar. Right? Because in that sort of system, you radiate away all of your perpendicular energy basically instantly, and you're in the lowest Landau level, and all you really care about is the parallel dynamics, which are fully described here by no approximation. In that kind of case, maybe you'd only keep L equals 0, so the 0th Fourier harmonic and the first 2 Laguerre polynomials. Then you'd have these sorts of evolution equations for the 0th and 1st Laguerre polynomials. These look nasty. These look even worse than where you started with the Blasov equation, but you no longer have a B perp, so you've reduced a 6D problem down to 4D. You've also reduced some of the fast cyclotron motion, so your time step can be larger. You do now couple to fluid moments, which you now need to describe, and you do need to solve a momentum equation and still Maxwell's equations. But because of the reduction of this problem, you get still full kinetics in the parallel direction. You've approximated by truncation the perpendicular motion. The system of equations is about 10,000 times faster than the Blasov. So you can actually do full global simulations of things, which is really quite impressive. Very proud of this. We'll have a paper out on this very soon. Actually, a series of papers. Anyway, also another ad. We have an NSF CSSI proposal with RPI and IU to create a science gateway featuring Jekyll. You can go to this website and actually run Jekyll in a browser window for some simple problems and plot data. We're working on expanding this to larger clusters so you can actually do real problems, but we're This is a really good teaching resource at this point. We think we even have auto-generating input files. Okay. Finally, results. Okay. So what we're going to do using Jekyll is, this is the blast-off, not PKPM. Throwing a lot of stuff at you, just to be clear. So full blast-off, we're going to do something similar to the GEM problem, the Geospace Environmental Modeling Challenge problem, which is just a Harris sheet. We're going to add a guide field to it. So that means the initial magnetic field profile is a pressure balance. We also add some noise to break symmetry, because when you don't have noise in a simulation, everything stays completely symmetric, and that's kind of boring, actually. So we start with the normal Harris sheet sort of profile for the magnetic field with guide field, initial layer thickness of half of the DI. It's going to be still a small box, but that's really all we need for this. 8 pi DI. And initial perturbation so that the X point stays semi-close to the center of the simulation. TI over T of 5, ion beta of 5.6. We're going to do reduced mass ratio because this is blast off, it's still expensive. Ratio of 25, reduced speed of light also. C over V alphane. The electron alphane speed is only 4. We're going to do a grid of 112 by 56 in configuration space. This is 2D. And 24 cubed in velocity space for both the ions and the electrons. With second order polynomials, so it's really 3 times this resolution. So it's more like 336 by, 168 by 72 cubed. We have finite extents in velocity space that go from plus minus 6 V thermal. That is sufficient for this problem. We are going to use a little bit of collisionality just to regularize things, because if you get too fine a structure in a blast off code, things can go a little haywire. This, I'm stressing, is a very weak amount of collisions. The electron-electron collision frequency is 1% of the ion cyclotron frequency. Just as an example, the temperature anisotropies you develop for the ions and the electrons, these are subtracted from 1. So red means excess perpendicular, blue means excess parallel temperature. So sort of similar-ish things as we saw in big simulation. We can look at the distribution functions. This is what the ion distribution function looks like at this point. It is just a single point. There's no need to average because we're directly solving the distribution. We're directly solving the class equation. This very bizarre shape that looks like a xenomorph pod from Aliens is actually just sort of a Gaussian or Maxwellian distribution function of the ions. And then this spread of stuff is pickup ions from coming upstream and being picked up by the flow coming out. We can look at the electrons at a point. Let's say look at them at x equals 0 at the X point, and we end up with this weird fungal looking thing, right? This is actually due to the electrons having Spicer orbits at the X point because they are actually being demagnetized. You can see the Spicer orbits of the electrons in these lobes. Okay. So it evolves like you would expect a reconnection to do. This is the out of plane current in color. You just develop a single X point because it's a small simulation. Since somebody asked, we have periodic boundary conditions on these ends and conducting walls on the top and the bottom. Just a single sheet. This is the reconnection rate as a function of time. Goes up, peaks around 0.2. It's a little bit higher than the canonical 0.1, but that's because it's a small box. That's pretty normal. You can also look at the change in the energy normalized to the initial total energy. For things like the total energy, which is the solid black line, which is completely well conserved. There's no loss of energy. Simulation. The dashed black line is the thing that changes the magnetic field energy. And then the dash dotted is the change in the thermal energy. Dash is the change in the flow energy. Red is for ions, blue is for electrons. So the electrons gain about 3% of the energy during the simulation. It's pretty typical. Finally, we can look at J dot E as a function of time. So the total J dot E is black, red is ions, blue is electrons. And the peak J dot E is at T equals 19, so that's where we're going to focus. Right. So let's first do this Lagrangian or guiding center energization analysis applied to this simulation. All right, so we have J dot E, that's the total energization, that's in magenta, curvature drift in red, the beta grad B term in blue, and parallel energization in green. And the sum of those three is the dashed. Looks pretty good, looks similar to the PIC result. There's some error here, especially T equals 19, but it's only like 20%. Seems promising. Now let's look at a cut at y equals 0 through the reconnection layer. Color scheme is the same, so this is total J dot E. Now we can see it at the x point itself. All you have is the parallel acceleration, kind of like what I showed in the 2D contour plots for the PIC results. But now red is the curvature drift again, and the dashed line is the sum. That looks nothing like J dot E, right? Looks terrible. This confused me for a very long time. I thought there was something wrong with my simulation, because I thought this should just work. But that doesn't work at all. So what's going on? This gives basically the same impression as the PIC results, where curvature drift is the dominant acceleration mechanism. In fact, it's gigantic locally. If you look at these different terms in the plane, so that's total J dot E, this is parallel, beta grad perp, and curvature. One of the main takeaways is the curvature drift is an order of magnitude larger than everything else, including J dot E. So if you sum it over everything, it just looks like the curvature drift and looks nothing like J dot E. It does have similar structure to the PIC results. You have large curvature drift out here where the islands are contracting. So I mean, things look consistent, but they really don't add up in a good way. Let's look at the Eulerian approach instead. So now we have more terms, but still magenta is J dot E. Red is this curvature drift, which is delta P U dot kappa. It's negative now. Yellow is polarization drift. Green is still parallel acceleration. Cyan is the agerotropic drift. And now the dominant global term is the diamagnetic drift, which wasn't even there in the guiding center approach. If we do a cut locally, I should say that the sum agrees almost perfectly. It's accurate within about 1% at t equals 19. If we do a cut at y equals 0, just like before, now we see that the sum and J dot E agree extremely well. The curvature drift is negative. Parallel acceleration is, of course, still the dominant thing at the x point. But now we see the agerotropic drift is actually the dominant local contributor, which means that the electrons aren't actually that well magnetized here. But this is a term that would be completely absent from any guiding center type of description. Okay, so those things. And if we look at that in the 2D plane, we have J dot E again. We have all 5 components of that equation. You notice the diamagnetic drift is large and positive almost everywhere, which is why it dominates the integrated sum. Curvature drift is pretty much negative everywhere. The agerotropic drift is large and positive throughout pretty much the entire reconnection layer. And polarization drift is positive, but it's small, so at an order of magnitude smaller than everything else. The sum of these now agrees almost perfect at every point in the plane. It's partly a statement that we've actually done this rigorously and not left out any terms. That's what we hope to see. We can do some of the other formulations for the Eulerian equations. So now this is separating out that minus P perp UE dot kappa term and grouping it in with this betatron term. So now this curvature term, unlike in the figure I just showed, was negative. This is now positive. This betatron term is now large and negative, kind of opposed to each other. I usually don't like to see things that oppose each other like that. This is what I said would more directly compare to the guiding center set of equations, and it actually does agree pretty well, except it's missing several terms of the energization. If we do cuts again, so this is the same cut I showed before for the guiding center energization, where the curvature drift is gigantic and the sum doesn't work at all. It works almost perfectly here, but as I said before, this curvature term that just depends on P parallel is almost perfectly opposed to the betatron term. That usually means you shouldn't separate the two terms. That means they're just working in tandem to cancel each other. We can do one last separation where we actually keep the diamagnetic and that beta curvature term separate. And globally, you can see that they really are just completely out of phase with each other. Same thing here, almost completely out of phase with each other, canceling, which to me says you should never separate these terms. They come together and work in tandem to cancel each other. So what can we say about all this? Okay, so guiding center analysis does not well model the Toyota station. That's because it's missing drift contributions. You could add things like polarization, but it would never have diamagnetic drift or agerotropic drift. And the frame transformation is incomplete, like I said. You've kind of moved into an Eulerian frame by summing over ensembles of particles, but you haven't done that in you were just following you were evolving particles, but you're actually trying to solve something in terms of guiding centers, but they're not actually guiding centers. The Eulerian description is rigorous and fully captures the bulk energization, meaning the flows, pressure, temperature. But there's ambiguity in how you group those drift terms, which is why I had a slew of equations that I threw at you. In any case, the Eulerian description suggests that the diamagnetic drift dominates globally with large local spikes of direct, meaning E-parallel, and gyrotropic drift energization. The full curvature drift depends on the pressure and isotropy, which, when you do that, yields little net energization. In fact, it was negative overall in this simulation. So does that mean the previous PIC studies are wrong? Does curvature drift actually not energize electrons like they've been saying for years? No, it doesn't actually. There's a subtlety here. The highlighted curvature drift regions are definitely still regions where you're accelerating particles. There's no way around it. If you have an electron that's streaming along a field line with a field line that's snapping back at you, you're going to get Fermi acceleration. So the curvature drift regions that are highlighted in the guiding center approach are definitely generating high energy particles. But the net energization can still be negative, because you could still pull out high energy particles, but you could lose energy from the core by, say, slowing the core down or cooling the core. So that even if you generate high energy particles, you might have cooled the plasma or slowed the plasma in bulk sense. This is what's been completely neglected from all of the PIC studies. So the guiding center approach provides insights about high energy particles, but the Eulerian approach actually gives you a really complete and rigorous perspective on the bulk energization and heating of the plasma. So just going to quickly conclude, I'm running out of time. So the Eulerian diagnostics and simulations provide a rigorous complementary approach to examine electron energization reconnection. I don't want to say that all of the big studies are wrong. It's just there are a lot of subtleties that have been neglected from them that lead to incorrect results. The Jekyll simulation framework that I discussed is a unique tool to study these sorts of things that enables Eulerian kinetic simulations. So you can do a truly Eulerian both simulation and analysis together rather than trying to switch between perspectives. And using Jekyll, we've identified the agyrotropic drift and direct acceleration as the dominant local energization mechanisms, but diamagnetic dominates globally. Curvature drifts can still lead to high energy electrons, but oftentimes the net effect is that it's an overall loss of energy. And as I said a second ago, the guiding center approach provides insights in high energy particles, while the Eulerian approach gives a complete perspective on the bulk energization and heating. And importantly, all of these tools and perspectives apply directly, the Eulerian tools and perspectives, I should say, apply directly to spacecraft measurements, in contrast to the previous guiding center approaches, which are very non-rigorous and missing many terms. Thank you.
Do we have time for some questions?
Yeah, thank you so much for this interesting talk. Actually, I have a question regarding this magnetic field reconnections. And what's the strength of the magnetic field around the reconnection? And I expect that it will increase because magnetic fields are squeezed to the small region now. And is it safe to consider that still the particles are following the linear Maxwell field equations, or we have to consider some non-linear effect also?
So when you reconnect fields, the magnetic field strength decreases because you've exchanged some of that magnetic field energy density for the outward flows and energizing the particles. I think that's what you're asking.
I mean, just before the reconnection also.
Oh, like in the reconnection region itself? Yeah, it's high there because you're squeezing the field in, right? As you squeeze the field in, it is higher on the edges of the reconnection.
Like charged particles still following the linear Maxwell equations, or like?
No, nothing I did was linear.
Okay, I saw like we are considering the Maxwell linear equations there.
Well, Maxwell's equations are linear, that's true, but the Blasov equation is not linear.
Thanks.
You mentioned the Galerkin method. Yeah. What's your base function for the expansion?
Good question. So we use Legendre polynomials basically. But we usually use serendipity polynomials, which is a way just to reduce the numerical complexity while keeping the same convergence order. Yeah. So serendipity, just ignore products of polynomials when the product order is larger than the order of polynomial you're using. So if you have say second order polynomials and you have x and y, so each one would have, when you square it, x squared plus x plus 1, it would ignore terms that are like x squared, y squared, and x squared, y, but keep x, y. That means you lose some points, but it has the same formal convergence order and reduces the complexity. Yep.
So you named your code after Dr. Jekyll, but you had an image that included
Yeah.
Mr. Hyde. So what's his role in this?
Yeah, so we don't use that joke as much anymore, but the joke is, yes, the unstable or development side of Jekyll is Hyde. The Jekyll team is actually quite large, order 30 or 40 people at this point, and about half of them are actually doing development tasks. And because, like I showed you, we have multiple different equation sets, it's very actively developed. I mean, we do everything from sorts of things I described to modeling fusion, modeling lab devices, global magnetosphere modeling, stability modeling, all kinds of fun stuff, plasma thrusters.
And then I'm also wondering, I mean, you briefly mentioned turbulence, right? And obviously the sort of, classic, I guess, Fermi geometry, right, is very clean. And then you showed how well you can get regions that look like that in a turbulent flow. But I guess sure I've heard other talks where it's like, oh, the nature of turbulent reconnection is inherently different from the non-turbulent picture. So I don't know.
It is.
Thoughts on that.
That's a really good question. Especially with Newtonian, like regular old turbulence and like the solar wind or something. I've never seen anybody claim that Fermi acceleration or curvature drift does much. It's even still a question of how much of a role reconnection really plays in dissipating the turbulence. That's actually a really major area of debate in the field. I won't say which side I'm on, but it's interesting when you move to relativistic turbulence, special relativistic turbulence. In this case, is really what I mean. There, you actually do generate high energy particles, and they're co-located regions where you have these sorts of Fermi acceleration or curvature drift looking regions. So it does seem to actually work to accelerate particles in relativistic systems in a very similar way to what I described here, but Newtonian systems don't seem to do that.
Can I just ask a clarifying question on one of your last bullet points on if the pick results are wrong? I couldn't quite get from that if you're saying that they've identified the right regions where the energization and the heating is happening, but they're not naming the mechanism correctly. Is it that they're not keeping correctly?
It really depends what you're interested in. If all you care about is energetic particles, I think the guiding center approach works pretty well, because that's going to highlight where you have particles that are good candidates for Fermi acceleration. If you're interested in the holistic picture, like what's actually happening to the plasma, is there a bulk flow? Is there heating here? Heating in a core sense, not just in generating a parallel tail. And it's missing a lot.
And it's missing, it's not just misnaming the mechanism, it's actually neglecting certain heating processes.
Correct. Yeah, the this is a little bit of the ambiguity of how things are grouped. There's a subtlety that I didn't want to go into here. It's actually in Goldston's textbook, if anybody wants to read it, chapter 7. And connecting guiding center drifts with fluid drifts. The guiding center drift is the p parallel thing that I described way back here. This one, yeah. The guiding center curvature drift looks like that, no question. Or I guess you go to this slide. This slide. Guiding center curvature drift looks like that. But again, that's the motion of the guiding center. There's actual particle motion too, right? If you add the particle motion in the frame in which the guiding center is at rest, you get the p perp term. So you actually do get the delta p when you properly account for the motion of the particle itself, not just the guiding center, which is why I said they don't actually do a complete transformation here between the two frames.
So one could evaluate that expression in the PIC codes and is that something that would be feasible to do or?
Yeah, I mean, you could, literally, it's that.
Okay, got it.
That is the correct thing to do. There have been multiple papers trying to figure this out, and they've all almost written this.
Mhm.
I don't know why nobody has.
I'm assuming this then will be written by you soon.
Yeah, I'm just waiting to hear comments from Greg.
Okay.
Thanks, everybody. Oh, go
Oh,
ahead.
yeah.
Again,
Yeah.
okay, so in reconnection between two magnetic islands, there is an X point. My question is, for example, in turbulence, there are lots of plasmoids and X points. In classical reconnection theory, we have a Sweet-Parker reconnection, Patrick reconnection. What type of reconnection is it between two islands?
So you ask an interesting question. I mean, kinetically speaking, you don't usually get Sweet-Parker reconnection. You don't get that long sheet. You get more X point Petrek style reconnection. So in turbulence, you do usually get X point reconnection, unless you're doing like MHD simulations or something. MHD will generate Sweet-Parker layers generically. Yeah.
Let's thank the speaker again. Would like to meet with Jason. There's still time. He's here through Friday. I sent the schedule out last your email several times. But if any of this is motivating, let me know and we can get your name added to the schedule.
A quick question.
I've
That's why